When you think of planets, chances are you're thinking of rocky worlds like Earth, Mars, Mercury, and Venus. And when it comes to planets outside our solar system, those with roughly half of Earth's size to twice its radius are also generally considered terrestrial. 2. Anything bigger is normally thought of as a gas giant. Of course, this terminology is somewhat arbitrary. There's no hard line between rocky and gaseous. Just ask poor old Pluto, demoted from planet to dwarf planet in 2006. Because it's too chatty with its neighbors. But hey, sometimes we find planets that are neither fish nor fowl. Enter the super-Earths, larger terrestrial planets that are at least twice the size of Earth, but still seem to be mostly made of rock. The first confirmed super-Earth was 55 Cancri, E, discovered in 2004, orbiting a sun-like star around 40 light-years away. Today, over 5,000 exoplanets have been found, and more than 300 are officially classified as super-Earths. But despite all that attention, we're still looking for our first clear signs of life elsewhere in the universe. Terrestrial planets are rocky worlds composed of rock, silicate, water, and/or carbon. They're usually relatively small, solid objects with either no atmosphere or a thin one. In order to determine if some of these worlds have atmospheres, oceans, or other signs of habitability, it takes more investigation. Larger terrestrial exoplanets, those at least twice as massive as Earth, are classified as super-Earths. Super-Earths are often difficult to characterize because they're so diverse and they often receive too little light from their stars to be studied with current technology. Because of this, they can be both incredibly hot or very cold. Some may have atmospheres, oceans, and even weather, while others might be frozen solid. Some may have oceans beneath their frozen crusts. Others may have vast oceans, and still others could be completely dry. In general, terrestrial planets have a bulk composition that is dominated by rock or iron and a solid or liquid surface. These faraway worlds may have gaseous atmospheres, but that's not a defining feature. In our own solar system, the definition of a terrestrial planet excludes any gas giants like Jupiter and Neptune, which are huge planets mostly made of gases like hydrogen and helium. Most models define the boundary between terrestrial and gas giants at about 10 times the mass of Earth. Exoplanets have been found that are as small as Earth and orbit very close to their stars. The existence of these planets confirms that many stars can have multiple planetary systems like our Sun. For now, scientists are still working on finding worlds in a Goldilocks zone, a region around a star where conditions are just right for liquid water to exist. We've found rocky planets in Earth's size range, at the right distance from their parent stars to harbor liquid water. This is known as the habitable zone. While these characteristics don't guarantee a habitable world, we can't quite tell yet if these planets really do possess atmospheres or oceans. Some researchers are studying small exoplanets to get clues about their atmospheres and habitability. Atmospheres can absorb and transmit light in specific wavelengths, providing information about what chemical elements are present. A new analysis of data from Hubble and Spitzer space telescopes suggests that a planet in the TRAPPIST-1 system lies in the habitable zone of its ultra-cool dwarf star. Scientists have been analyzing the system since 2017. The system consists of at least 7 rocky planets. 3 of them could have conditions suitable for liquid water, but they are tightly packed near their star, raising questions about their atmospheres. In February 2018, a closer look at the 7 planets suggested that some could harbor far more water than the oceans of Earth, in the form of atmospheric water vapor for the planets closest to their star, liquid water for others, and ice for those farthest away. That research pinned down the density of each planet more precisely, making TRAPPIST-1 the most thoroughly known planetary system apart from our own. It's impossible to know exactly how each planet looks, because they are so far away and so faint compared to their host star. In our own solar system, the Moon and Mars have nearly the same density, yet their surfaces appear entirely different. Based on available data, here are scientists' best guesses about the appearances of the planets. TRAPPIST-1b. The innermost planet is likely to have a rocky core surrounded by an atmosphere much thicker than Earth's. TRAPPIST-1c also likely has a rocky interior, but with a thinner atmosphere than Planet B. TRAPPIST-1d is the lightest of the planets, about 30% the mass of Earth. Scientists are uncertain whether it has a large atmosphere, an ocean, or an ice layer. All 3 of these would give the planet an envelope of volatile substances, which would make sense for a planet of its density less than half that of Earth. Scientists were surprised that TRAPPIST-1e is the only planet in the system slightly denser than Earth, suggesting it may have a denser iron core than our home planet. Like TRAPPIST-1c, it does not necessarily have a thick atmosphere, ocean, or ice layer, making these 2 planets distinct in the system. It is mysterious why TRAPPIST-1e is so much more rocky than the rest of the planets. In terms of size, density, and the amount of radiation it receives from its star, this is the most similar planet to Earth. TRAPPIST-1f. G and H are far enough from the host star that any water they might possess could be frozen as ice across their surfaces. If they have thin atmospheres, they would be unlikely to contain the heavy molecules of Earth, such as carbon dioxide. If a planet has an atmosphere, it can tell us if it has oceans, and even hints at whether the oceans have waves. Let me explain. Waves move through mediums like air, water, and even light by causing oscillations that transfer energy without transferring matter. If a planet has a substantial atmosphere, the resulting wave-like oscillations could cause variations in the amount of light passing through it. By measuring the fluctuations in light as a planet moves in front of its star, scientists could determine whether the planet has a substantial atmosphere and whether that atmosphere is gassy or more dense. If the medium is dense enough, it can support large waves, meaning it could have oceans. One of the best ways to search for planets is by looking for the dimming effect that occurs when a planet passes in front of its star. If that dip in brightness lasts longer than expected, it might mean the planet has an atmosphere. Now, not all planets have atmospheres, and some atmospheres are opaque. However, scientists believe that a planet that is close enough to its star to be hot enough for life to evolve might also have an atmosphere, so it is worth investigating these candidates further. As for planets that are farther from their stars, the water on them should be frozen, but there might still be activity beneath the icy surface. Scientists speculate that heat from the planet S core could keep the bottom layers of ice as a liquid. Tidal forces from the star could also cause friction, generating heat that could keep water beneath the ice shell liquid. In general, super-Earths are believed to be good candidates for the search for extraterrestrial life, because many are thought to lie within the habitable zone of their stars. However, astronomers are learning that super-Earths come in a variety of forms, and not all are suitable for life. The discovery of WASP-33b, a 2.2 times Earth-sized planet that orbits a Sun-like star, brought super-Earths into the spotlight. WASP-33b was thought to be in the habitable zone of its star. However, its scorching temperatures suggested that it instead had a thick, hot atmosphere. Since then, follow-up studies have shown that many super-Earths may be unlivable due to high temperatures, extreme radiation, or the complete absence of an atmosphere. It's not all bad news, though. Scientists have been discovering other super-Earths that are smaller and more similar to Earth than WASP-33b. They tend to orbit red dwarf stars, which are much smaller and cooler than our Sun. Gliese 667cc is a 3.5 times Earth-sized planet that orbits a red dwarf. Its star receives about one-third the amount of radiation that Earth gets from the Sun. Therefore, it could have liquid water on its surface. Another promising candidate is Kepler 442b, a 2.4 times Earth-sized planet that orbits a slightly smaller star than our Sun. If a super-Earth had a strong gravitational pull, it could hold on to much more water than Earth.